the audio is better there. But for now, we'll carry on. And it's a pleasure to have Alex Smith from Clay Math and UCLA to give his first talk in his lecture series. And this one is on Selmer groups and the Cassels pairing and
bunch of stuff. Yeah.
bunch of stuff.
Thank you.
Yeah.
Yeah, thank you for the introduction. It's great to be here. Thank you to the organizers for putting this together. This is really exciting. So today I want to talk about, I want to introduce my style of arithmetic statistics. And Tristan did a really good job sort of setting up the stage in terms of elliptic curves. And the key families, for me anyway, have always been the quadratic list families. That's what we'll start with, is just talking about quadratic lists. And so the construction here is, suppose we have an elliptic curve with some Weierstrass form, y squared equals x cubed plus x plus b. And for this to be an elliptic curve, we need 4a cubed minus 27b squared to be non-zero. Now we're going to assume that this is over the rationals, so a and b are rational numbers. Then given any non-zero rational number d, we can define the quadratic twist of this curve EV just by putting a d out front. And yeah, I should definitely name this curve called E. And so this defines an elliptic curve which is isomorphic to our original curve geometrically, but it typically does not descend to something defined over Q. And to be more specific, we have a map that I like to call beta, going from the quadratic twist to E. And this is a geometric map that doesn't descend to Q. So this sends xy to x root dy. And you can check that if xy is on the curve ED, then x root dy is on this curve, on the curve E. Okay, and so I keep saying, yeah, this isomorphism isn't defined over Q. And so one way to check that is to check how this map beta d interacts with the Gala action. And so, so suppose we're given some sigma inside the absolute Gala group of Q, which I'm just going to denote by GQ. And so what I'm going to do is, looking at this point xy, I'm going to compute sigma of beta d xy. Okay, so sigma beta d xy, well, beta d just maps to sigma to root dy on the right-hand side. This is in turn, the sigma just comes inside, so it becomes sigma x, and then sigma of root dy, which is just sigma of root d, sigma of y. Okay, but coming from the other side, we could be looking at beta d of sigma xy. And if we look at what this is, we see that this is going to equal, I've given myself slightly not enough space. Yeah, so this is equal to sigma x, and then root d sigma y. Okay, so if this map were equivariant, this would equal this. But you can see that they're not quite the same. There's this, instead of a root d here, you have a sigma root d. And so the difference between these is given by a sigma root d over root d term that shows up here and here. Now, sigma root d over root d defines what's known as the quadratic character associated to the square root of d. So let's say chi d. We have this map associated to d going from dq to plus minus 1, defined by chi d sigma is equal to sigma root d over root d. And so to summarize what this calculation says that sigma of beta d of z is equal to chi d sigma times beta d sigma z. And this holds for all z on the elliptic curve EB and all sigma inside of GQ. We have a twisted equivariance relation. And in fact, this is the proper way to define what a quadratic twist is. A quadratic twist should be some functor defined on modules such that the module that you get after twisting can be related using a map beta d like this, obeying this relationship. So you can define quadratic twists for Galois modules more generally using this. And this is the same description. This identity also works for, say, quadratic twists of abelian varieties, that sort of thing. Okay. And so one consequence of this that should be fairly clear is this implies that the two torsion of ED is isomorphic as a Galois module to the two torsion B. And the reason for this is when we consider the action of the Galois action on the two torsion of E, that Galois action is related to the Galois action on E2 using this relationship. But chi d sigma is always equal to 1 mod 2. And so this chi d sigma does nothing on these terms. And so the result is that, beta d is an equivariant isomorphism between ED2 and E2. And so this is so important that I'm putting it on the board before I even state my main theorems or anything about arithmetic statistics. This relationship is sort of the keystone to everything. Okay. Now that I've made that clear, next want to write down something statistical. So here's a conjecture. Given any E, the analytic rank of E twisted by D is equal to 0 for 50% of D. It's equal to 1 for 50% of D. And it's anything larger for 0%. To be more precise, what this is saying is consider the set of integers between negative x and x such that the analytic rank of ED is equal to 0. Then as x gets larger and larger, that proportion limits to 50%. And similarly, the proportion for 1 limits to 50% as x gets larger and larger. And most confusingly, this portion limits to 0. So this is a negligible set over the set of all integers. So this was originally conjectured by Goldfeld back in 1979. And it's sometimes known as the minimalist conjecture because it's conjecturing that rank is as small as possible 100% of the time. And if you just look at this, that might be a little silly looking because the smallest one is 0, but a lot is at rank 1. the reason for this has to do with the L functions that Tristan defined at the end of the last talk. And specifically, if you look at the L function for ED, you have a functional equation which relates this to the same L function but for 2 minus s. Where this term here is what's known as the global root number. And lies inside plus minus 1. I may be missing some fudge factors to actually make this work. But what ends up happening is to determine the global root number, as in the sign of this functional equation, this can be done locally. So you figure out what the local root number is for each place V, and you take a product, and that defines WVT. And so, yeah, you're able to figure out what this is just from how D behaves locally. And you can also prove that W is equal to plus 1/2 the time and minus 1/2 the time. So half the congruous classes lead to plus 1/2 to minus 1. And when it's plus 1, the order of vanishing of this L function at s equals 1 has to be even. And when this is minus 1, the order of vanishing has to be odd. And so because of that, this really is the minimalist conjecture. What this is saying is that on 100% of cases, the analytic rank is as small as is permissible given the global root number. And so to state my main theorem, what I was able to show was that this conjecture follows from the Burton-Swinnerton-Dyer conjecture. With the final set of curves that I need to handle being handled earlier this year. And so this isn't really a state. The actual method for proving this isn't based on the Burton-Swinnerton-Dyer conjecture. Basically, the reason I want to use BSD is to get a handle on the analytic rank, because the actual ranks that I handle, the things that I really am trying to control, are not the analytic rank, and they're not the Mordell-Bay rank, but they're instead a rank that only showed up very briefly in Tristan's talk when he mentioned P-converse theorems. What I try to control are what are known as 2 infinity Selmer coranks. And so to explain that, I need to talk a little bit about Selmers. Okay. So as Tristan mentioned in his talk, we have a nice group structure on our elliptic curves. And this group structure is actually how we're able to do descent on them to control the rational points so well. And the starting point of this is we can take a look at the exact sequence taking the n torsion of E into the full elliptic curve. Let's say it's a set of algebraic points. And this is exactly the kernel of the multiplication by n mass. Excuse me. Great. And so this is something that we'll look at for n greater than or equal to 2. Okay. And so this fits in, this gives us a sequence of Galois modules. So these are each modules with a structure of a GQ action on them. And yeah, to get that for these, just think of the Q bar points. And so because they have that group action, we can consider the long exact sequence in group cohomology. And so the part of that sequence that I need starts with the H0 term of E. So H0 GQE maps into H0 GQE. So it's the multiplication by n. And this goes to H1 GQ EN. And this, let's go one further, goes to H1 GQ E. Okay. So I'll talk a little bit about how these are defined in just a minute. One thing that you should definitely remember about group cohomology is how to interpret what the H0 is. In this case, H0 is going to be the set of invariants. And so what are the invariants of the Galois action on the elliptic curve? These are precisely the rational points. So this is just EQ. And we have a multiplication by n map going from EQ into EQ. And the sequence is exact. And it maps into H1 EQ EN. Okay. Now, in addition to this picture, the relevant structure that we need to understand Selmer groups is to look at the corresponding picture locally. So for each place V, in addition to the Mordell-Veit group, we look at the points in QV, or defined over QV. So this would be the p-adics, or the real points of our elliptic curve. And so we have the same picture on bottom. And here, GQV is the absolute Galois group of the completion of Q at V. I'll sometimes just write this as GV. This is pretty standard for thinking about local conditions. And so one observation to make is that if you have something in the image of EQ inside of H1 GQ EN, then when you project that down to H1 GQV, that's going to be in the image of EQV. And this just comes from going around this diagram in two different ways. And so one consequence of that is from this diagram, what this gives us is this gives us an injection of the Mordell-Veit group into the kernel from H1 GQ EN, mapping into the product over all places of Q of H1 GV EN. And then module of the image of EQV under this connecting. Okay. And so this is really useful, actually, because this group is very important. This group encodes the rank of our elliptic curve. And meanwhile, this group, I know it looks like a bit of a hairy definition, but this is a finite group. And this set, H1 GQ EN, is something that we can actually parameterize pretty readily. And so this is something we can get our hands on. And so using sequences like using this inclusion is actually the only real way we have for controlling the rank of elliptic curves. This object that I've written down, this kernel, is what's defined to be the Selmer group of the elliptic group. And so the main goal of my work is to understand how Selmer groups behave in various families of elliptic curves. Okay. So just to write down one more definition that will make things convenient, let me say that Rn of E is going to be the maximum R such that Z over NZ to the R injects into the N Selmer group of B. And I'm actually going to do something controversial here and get rid of all the torsion points because they stink. They kind of make the statistics just strictly worse. So it's convenient to just get rid of them immediately. And even when we do this, we get the crucial results for Rn of E, which is that Rn of E is always an upper bound for the rank mean. This is why we care about Selmer groups in the first place, that they obey this property. A second property that I'll mention is one that's very relevant for my work, which is that if you look at the powers of 2, these actually give us a non-increasing sequence of rings. So R2 is no smaller than R4, is no smaller than R8. And I'm just going to take the limit of these things to be R2 infinity. This is what's known as the 2 infinity Selmer corank of E. And this is also an upper bound. And this fact is a conjecture, so it's not actually a fact. That's okay. If you believe the Tate conjecture, the 2 infinity Selmer corank of the elliptic curve should actively be his rank. But the idea being that otherwise your Tate group has a copy of Q2 over Z2 in it. Okay. And one final fact that I'll write down is that if we look at the parity of the analytic rank of our elliptic curve, this actually matches the parity not just of the 2 infinity Selmer corank, but of the 2 Selmer rank and the 4 Selmer rank, and so on. And we'll talk a little bit more about this in just a little bit. And so now that we have this notation for Selmer ranks, I can give my theorem more properly. And so what the theorem actually says is that as D varies, so we fix an elliptic curve as before, and as D varies, the 2 infinity Selmer corank of E is equal to 0 for 50% of D. Is equal to 1 for 50% of D. And is anything larger for 0% of D. Let me just give why this implies that B is steady applies Goldfeld's conjecture. So how this argument works is suppose BSD holds. Then what that tells us is that the rank of our elliptic curve ED, this has to equal our analytic rank. But this is also at most equal to the 2 infinity Selmer rank. And we also know that this analytic rank is equal mod 2 to the 2 infinity Selmer rank. So we have this string of facts. And so if we also know that the 2 infinity Selmer rank is equal to 1, well then the 2 infinity Selmer rank is 1 here, and then that implies the analytic rank is 1, because that's the first number that's odd, or the first non-negative integer. And so we have a sandwich that the analytic rank equals the rank equals the 2 infinity Selmer rank. And similarly, when the 2 infinity Selmer rank is 0. Now, ideally, you should notice that BSD is actually a really strong thing to assume to imply Goldfeld's conjecture. Sorry, does anybody have questions?
Do you still need BSD you wanted to prove the algebraic?
Yes, you would. Yeah. So if you wanted, so the question is, if you wanted to prove this for algebraic rank, for Mordell Bay rank, would you still need to assume BSD? And the answer is currently yes. The idea being that I'm unable to show that if something has 2 infinity Selmer rank 1, it's not impossible that its rank would be 0. Now this is not true. Like BSD is true, and if BSD is true, then we're fine. But like, yes, ostensibly there could be examples where the 2 infinity Selmer rank is 1, but the rank is 0 without assuming BSD.
Because in that case, you get away with like finiteness of Shaw.
Finiteness of Shaw would also work. Yeah. If you care about algebraic rank, you can assume finiteness of Shaw. I think there's parity conjectures, which also give some form of this. My favorite is these p-converse theorems, which Tristan mentioned, and these have been proved in some cases which are relevant. You can imagine this whole construction going through for a different prime besides 2. And what a p-converse theorem says is, suppose you have an elliptic curve PE and a prime P, and they satisfy some conditions. So just there's a bunch of these. The conditions range from very reasonable to very tricky. But in each of these cases, the conclusion is that if you have that the P infinity Selmer corank is at most 1, that implies that the rank E is equal to the P infinity Selmer corank E. Basically, that the 3 analogs for the rank that we have are all equal. So the first of these are sort of the one I always think about. The archetypal example of the p-converse theorem was proved by Skinner and Urbon in 2014. Though I guess the first examples of these are due to Rubin for some CM curves. Anyhow, they're known in a lot of cases, but very few of them are known for 2 infinity Selmer groups, especially in quadratic twist families. So not much use for proving something like this unconditionally yet. Yes?
Is there a elliptic curve with a quadratic twist that has that right with that? Like are there examples that
Oh, yes.
0%?
Yeah, it is definitely non-empty. One fun fact that I always like mentioning is the highest analytic rank that we can prove an elliptic curve has is 3. So there's loads and loads of curves out there of like, obviously Noah Melkes has curves of rank 28, him and Zev have one of 29, but those are algebraic rank. Analytic rank, because of the definition in terms of L functions, and sort of the relative lack of theorems, like we only have Gross-Zagier, Coley-Vaughan, these sorts of things. We only know proved analytic ranks up through 3, but you should be able to find analytic rank up through 3 in pretty much any quadratic twist family. Great. Anything else before I continue? Okay, so the proof of this theorem breaks into two parts. The first part is to understand the distribution of two Selmer groups in these twist families. And then above that, for each set of elliptic curves with a given two Selmer structure, the goal is to understand the higher Selmer ranks. So the 4 Selmer ranks, 8 Selmer ranks, etc. And one tool that makes this possible is something that Ariel will talk a little bit more about on Friday. But it's something called the Cassels-Tate pairing. And this goes back to work of Cassels from the early 60s, maybe 1962. And so this says given, let's say, an integer n greater than or equal to 2 and an elliptic curve. There is a pairing between the n Selmer group of E. And I still really hate the Torton part, so I'm going to get rid of it. Yeah, there's a pairing between these two Selmer groups that is alternating. Whose kernel is equal to the portion of the n Selmer group that lifts to the n squared Selmer group. And so because these pairings exist, you can imagine, think of the case n equals 2. If you care about the distribution of 4 Selmer groups in a family, you don't actually need to construct all of those 4 Selmer groups. What you can instead do is construct the 2 Selmer groups and then figure out what the 4 Selmer group is by looking at the Cassels-Tate pairing in that family. And this is a really valuable perspective. I'll mention the reason that Cassels was interested in proving this is a corollary of the existence of such an alternating pairing is that these Selmer ranks that are defined before are in fact all equal mod 2. The idea being that if you have a alternating pairing defined over a field, the image of that, and you imagine it as a matrix, the image of that matrix is going to have even dimension. So the difference in dimension between the kernel of this pairing and the domain is even. And so you can imagine applying this for the 2 Selmer group gives you that the 4 Selmer group has an equal dimension, etc. Maybe it's a little bit trickier for the higher ones. So let me make this a little bit more explicit. This is a definition of the Cassels-Tate pairing, or of a variant of the Cassels-Tate pairing that I find very useful, which is given k greater than or equal to 1, we're going to define the Cassels-Tate pairing on layer k for the curve E. And the difference between that pairing on the left and the pairing I'm defining now is I'm going to put these 2 to the k minus 1 terms in front of each of my Selmer groups. So otherwise, this is going to be exactly the same. And the definition of this is going to be to just say that we're taking the Cassels-Tate pairing at level k of the elements 2 to the k minus 1 times phi and 2 to the k minus 1 times psi. This will just be the Cassels-Tate pairing as defined by Cassels for phi and 2 to the k minus 1 psi. And so your first, the first thing you should notice is that you would need to check that this is well defined. In the sense that many different phi may give the same value of 2 to the k minus 1 phi. But this is, in order to check this, what you have to do is you have to notice that this term is actually always equal to 2k minus 1 phi times psi. So these are equivalent. And so because both of these are equal for any sorts of phi and psi, you find that the choice of phi and psi doesn't actually matter. It doesn't affect what the pairing is. So it's well defined. And the other key property of this is that the kernel of it is going to equal the 2 to the k plus 1 Selmer image divided by the image proportion. So to summarize, a CPPK E is an alternating pair on F2 to R2 to the KE. So it's an alternating pairing on a space of dimension R2 to the KE. The kernel of dimension of R2 to the K plus 1 E. So if we can control all of these CTPKEs, that will give us control for all the higher Selmer groups. And so that's basically the goal, is to understand what these look like. And our expectation should be that as D varies, CTPK ET behaves like a random, or I should say a uniformly chosen random alternating pairing on F2 to the R2 to the K. And you should definitely quibble with this. Like, what does it mean for this pairing whose domain is changing to behave randomly? But it actually turns out that trying to address that issue helps a lot with actually proving the heuristic. So now I can state sort of the finer version of the theorem I wrote up earlier, at least in some cases. Okay, so just a bit of notation. I'm going to use this term P alt of J given N. This is going to be the probability a uniformly selected n by n matrix that's alternating over F2 has kernel of dimension J. Okay. Then if we're looking at an elliptic curve with no rational two torsion, we have that the probability as you vary d that the two Selmer rank of ED is equal to R2. The 4 Selmer rank is equal to R4, the 8 Selmer rank is equal to R8, etc. This is going to equal first a probability giving the distribution of two Selmer ranks. This is done as some limiting process for large alternating matrices. So that handles the two Selmer rank, and then the heuristic kicks in after the two Selmer rank. So the probability that the 4 Selmer rank is R4 is just given by P alt R4 2. This sort of measures. This is consistent with the idea that CTP1 ED behaves like a random alternating matrix. Next up is P alt R8 given R4, which is consistent with CTP2 being a random alternating matrix, and so on forever. And we expect, and this holds for any non-increasing sequence of integers. And so the observation from this theorem that lets us conclude the previous one, at least for elliptic curves with no rational two torsion, is that this probability is only non-zero if this sequence R2, R4, R8, etc. limits to either 0 or 1. If it bottoms out at, let's say, 2, then what you find is that every sufficiently, this sequence here, this product, has infinitely many 1/2s in it. So you end up with the infinite product of 1/2s. This ends up being 0. And so, yeah, this gives us this result from both. Now, outside of this case, another, you might ask, oh, is this how things behave in general? Yeah, so this theorem holds, also holds if E has full rational two torsions. And E has no cyclic rational 4 isotony. So in this case, you get exactly the same distribution of 2 of the K-Selmer groups for each K. And I'll mention that theorem holds in this case, and it holds in exactly no other cases. So for any elliptic curve that either that has a rational two torsion point and which doesn't fit into this specific case, you expect a different distribution of 2 infinity Selmer groups in the quadratic twist family. And I'll get into how that happens tomorrow. The issue in all the remaining cases is there's some isogeny whose Selmer group in the quadratic twist family contributes, leading to problems at the 2 Selmer level. And so in order to handle those curves, we need to separately calculate what the distribution of 2 Selmer groups is, and then somehow get back on track later in the sequence. And so instead of getting exactly this result, we only start seeing these p alt terms that we like, maybe starting at bar 8. So we're still able to get the to infinity result, but we have a different result earlier on. I'll mention that in these two cases, this is the distribution of to infinity Selmer groups. Constructed by Bargava, Kane, Leinster, Punin, Rains. And then also earlier by Delon. So yeah, in some cases, this heuristically understood set of to infinity Selmer groups is what you see. But then in other cases, we get something else. Which isn't to say that either of these sets of authors made an error. The Bargava, Kane, Leinster, Punin, Rains heuristic explicitly was avoiding quadratic twist families because they knew things like this could come up. The last thing I want to touch on today is I want to explore why we should expect, or why 2 is a good place to do these things. So why am I looking at the to infinity Selmer groups? And the answer for this starts with the definition of group cohomology. So let me go ahead and define that. So this group comes up a lot in what we're talking about. So let's actually define it properly. How you define the first cohomology group is it's defined to be the set of one cocycles with coefficients in En divided by the set of one coboundaries. And so the one cocycles, I remember when I first learned what they were, I was like, this is not important, but it is in fact important. So I know it looks silly, but it is a really crucial definition. The set of most one cocycles are the set of continuous maps going from GQ to EM. Here, continuous just means that there's some number field over which this map is 0. So it's a set of phi going from GQ to EN such that phi of sigma tau is equal to sigma phi tau plus phi sigma for all sigma and tau at this inside of GQ. That is the definition of one cocycle. This condition is sometimes known as the crossed homomorphism condition. You might say if En is a trivial Galois module, so sigma acts trivially, every sigma acts as the identity, then this condition is just saying that phi is a homomorphism. And this is actually a really important example to keep in mind, that if En has a trivial Galois structure, the one cocycles are just homomorphisms. The one coboundaries matter much less, but they are still important. And they are the maps of the form sigma goes to sigma minus 1x, where x varies inside of En. And so, yeah, I don't have much to say about those, but the top really does matter quite a lot. Okay, and so the reason why we're starting with the 2 Selmer group goes back to the equation that I boxed right at the very beginning. So that said, was E2 is isomorphic as a Galois module to E2. So these are the same as Galois modules. And so what that means is that if you have something valued in the 2 torsion of E, that obeys this condition, you can also think about this element as lying in the set of cocycles for any of the quadratic twists. So yeah, cocycles are shared between all of these twists. So what this implies is that H1GQ E2, we have a canonical isomorphism between this and H1GQ of ED2. And the reason this matters so much is we're interested in the statistics of the 2 Selmer group as D changes. And so what this tells us is that the 2 Selmer group of ED can be given as the kernel of a map from a fixed parameter space, H1GQE2, a fixed parameter space with like a very concrete description, to a product over all places. And then the only part of the definition that depends on E are the set of local conditions that go down here, which I'm going to denote using script L in this talk and then the next talk. And so the 2 Selmer group only changes because this part changes. And so in order to understand the distribution of 2 Selmer groups, what you need to understand is how, first, how these groups are changing and how that impacts the statistics of the 2 Selmer groups. And so I'll talk a little bit about how those calculations really are done, starting in tomorrow's talk. And I'll also do it on Thursday. So that's half of the battle of understanding the 2 Selmer group. For the 4 Selmer group, things are a little bit trickier because this will no longer apply. The 4 torsion of E and the quadratic twist of E are different. And so what you instead have to use is a sort of crazy fact to try to actually take advantage of. But if you have 2 integers, D1 and D2, non-zero integers, and you multiply them together, and you look at the quadratic twist associated with that and look at its 4 torsion, what you can prove is that this is a subquotient of E4 plus ED14 plus ED24 at the Galois module. Okay. And so we don't get the nice situation that we have in 2 Selmer group land, where we can compare 2 Selmer elements between different twists. That no longer works. What we can do is, if we have 4 Selmer elements at 3 different twists, we can sometimes smush them together to get a 4 Selmer element at the 1 remaining twist. This is sort of the central algebraic idea that allows the higher work to be possible. And then this is just for 8 Selmer groups. You have to have 7 twists on this right-hand side. So all vertices of a cube except for 1 at the 1 remaining point. You get, you have an 8 Selmer element at 7 twists, smush them together, get something at the 1 remaining point, which will be something of the form E D1 times D2 times D3 8, etc. And so I'll get into a little bit of how this works on Friday. Okay, so that's an explanation of why 2 is so important. It's because at the bottom we have an isomorphism of Galois modules throughout the family that we can take advantage of, and then we can build up from that to say something about the higher Selmer. And how I want to end is I just want to emphasize that this property that I've described at the end is not something intrinsic to. And in fact, this property is the important part rather than the fact that it's two. And in order to explain this, I want to look at a cubic twist family. So I'm going to take E sub D to be the elliptic curve y squared equals x cubed minus d squared. So this is a J invariant zero curve. It has Cm by z root negative 3. And so when you consider multiplication by root negative 3 acting on this curve, what that does is it defines a degree 3 isogenate square root minus 3 to a curve that I'll just call E prime D. And this has equation y squared equals x cubed plus 27d squared. So this is a cubic twist family of elliptic curves. Okay. And so if I were to box something about these curves, it would be the fact that as D changes, the kernel of multiplication by root negative 3 stays constant. So we have Galois equivariant maps between the kernel of square root minus 3 for this curve and square root minus 3 for any other curve in the same band. Now, one difference between this case and the previous case that I want to mention is that the 3 torsion in this cubic twist family is not preserved through a cubic twist. So so long as D is not a cube, these are not isomorphic modules. And so how I like to think about the story is that in this case, the square root minus 3 Selmer group is in it is an analog for the 2 Selmer group in the quadratic twist family. And similarly, the 3 Selmer group is an analog for the 4 Selmer group in the quadratic twist family. And so because of this, we actually can use the same techniques for studying the 3 infinity Selmer groups in this family that we use to study the 2 infinity Selmer groups in the quadratic twist family. And this is something I did with performance. For technical reasons, we didn't get that far. We only were able to say something about 3 Selmer rings, and I guess sometimes 3 root 3 Selmer rings. But what that tells us is that as D varies, and we look at the 3 infinity Selmer ranks in this cubic twist family, this is equal to 0 for at least 31% of D. Is equal to 1 for at least 47% of D. And is greater than or equal to 2 for at most 22% of D. And so, yeah, this is an example that shows that 2 doesn't always have to equal 2. You can, in fact, make progress using these style of methods at other primes. It's just that the prime has to match what you're twisting by. Okay, so that's all I want to say for today, and I'll be back tomorrow to tell you about 2 Selmer groups. Yeah, absolutely 50-50. So I'll say our interest in this was pushed because Bargava, Schnittman, and Alpage figured out the two Selmer average size of the two Selmer in this family. And they were able to make progress on both this 0 and this 1, not just in a to infinity Selmer rank, but also in regular rank. Ideally, yeah, I think the expectation both on our end and on their end is to get 50-50 eventually. But this, yeah, this is a complicated example, so we haven't gotten that far yet.
Do you work out any other examples for Gillian varieties besides Selmer?
Sorry, any for
Like here, like curves about like quadratic with
yeah,
or other Gillian varieties, you have a lot of other types of cliffs.
yeah, no, okay, this is a great question. So a result that I can tell you is that if you have an abelian variety that's like sufficiently general, and you consider its rank growth over cyclic quintic fields, in 100% of cases, this rank growth is at most 1. So that's something that's within what my methods can show. The expectation is that, except in the quadratic case, the rank growth should be 0 in 100% of cases. But there are complications that sort of plague these higher twist families. Like we sort of had to push through those to make progress here, and there's still complications that remain. Yeah, there's a lot to do, but it is already very hard.
There an analogous for J equals -20?
Oh gosh, probably. I can recall ever thinking about this in my life. So this would be looking at the quartic twist family. Yeah, I think that's an interesting question. It's something that I wish I had I wish I could remember what I had thought about it at some point. But it is currently unanswered. But it should be amenable to this sort of analysis.
Thank you.